Let's continue the lesson 10.1 about the second one, London dispersion forces, LDF, represented by LDF. It's weak and short-lived. It's weak, short-lived, but can be significant for large atoms. So dispersion basically forces are attractive forces that attracts basically as a result of a temporary dipole in an atom of molecule. Okay? So dispersion forces exist among species of all types, whether they are neutral or bear a net basically charge, and whether they are polar or non-polar. Okay? So polar and or non-polar. Let's move to the other slide basically. Okay, concerning basically the LDF in atoms or non-polar molecules. What is the meaning of it? Let's start by the strength of London dispersion forces depends on the polarizability of an atom. Polarizability, what is the meaning of it? It's when the electron distribution in an atom or a molecule can be distorted. It means what? Change their distribution unevenly into a instated dipole. So it means it lasts for just tiny fraction of a second. Okay? So we usually assume that the electrons of an atom are uniformly distributed about the nucleus. A short-lived, non-symmetrical electron distribution can develop that this produce a temporary dipole arrangement of a charge. So the formation of this temporary dipole can in turn affect the electron distribution of neighboring atom, that is this thing that we are talking about before. So it occurs accidentally in a given atom, can then induce a similar dipolar in a neighboring basically atom. So as number of electron increase, the number of electron increase, the polarizability will increase, the boiling point will increase. Okay? That it should be basically memorized. We should memorize it. Okay? On the other side, when we have a small atoms and molecule with their electrons tightly held near to the nucleus, it has a low polarizability. When we have large atoms or a molecule, okay, it has basically a high polarizability with loosely held electrons. Look at the picture as we can see. We have the tendency of an electron cloud to distort is called polarizability. Look, we have atom A, atom B. We have atom A and atom B in each case. And we have the polarization view. As you can see in the first one, atom A and atom B, for each one, okay, we can know basically the difference of each one of it. Okay, so when we have a small atom and molecule, we have low polarizability, to recap everything. When we have a large atoms or molecule, we have a high polarizability. And something we should know also, when the number of electrons increase, the polarizability increase, and the boiling point also will increase. Let's move to the LDF and physical properties. Polarizability enable gases containing atoms or non-polar molecule like N2 to condense. Okay? At a very low temperature and reduced atomic speed, dispersion forces are very strong, enough to hold He atoms together, causing the gas to condense. Okay? As the number of electrons increase, the polarizability increase, so dispersion forces also increase and the boiling point will increase. Look at the picture. We have between these two things, we have a weak attraction between each one of it. Let's analyze the table basically here. We have He and EAR and Kr, noble gas. The number electron of He it's 2, Ne it's 10, Ar it's 18, and the Kr it's 36. Okay? The molar mass of each 4, 22, 39, 83. Look at the boiling point. When the molar mass, it will increase, as you can see, molar mass increase, we have the boiling point also increases. Okay? Regarding, of course, the number of electron, it will increase also. Moving now to the dispersion forces, usually increase with the molar mass, as we said before, because molecules with large molar mass tend to have more electron, which is logic, and dispersion forces increase in strength with the number of electron also. So in addition, when we have a larger molar mass, often means bigger atom with electron distribution is more easily distributed because outer electrons are less tightly held by the nucleus. Look at this table. We have a compound, for example, we have CH4, CF4, CCl4, CBr4, and Cl4. Let's analyze this graph. We have the melting point of each. As a conclusion, what we can say? As a conclusion, look, when we have CH4, it has the lowest melting point. CF4, it will start to increase. CCl4, it will increase. And CBr4, it will increase. When we don't have basically any other element, we have an increasing of the melting point. It will reach to the 171 as a melting point. So again and again and again, when we have a higher molar mass, we have increasing basically of the forces, and we have increasing of the number of electron. So for that reason, we will have also increasing in the melting point also. Something we should mention about the thing that we are talking about. In molecules with a great number of electrons, dispersion forces are comparable or even greater than dipole-dipole forces between a polar molecule. Example, if we have CH3F and we have CCl4, okay? We have the temperature basically of the boiling point, it's minus 78.5, and it's basically 76.5 for the CCl4. Also, CH3F has a dipole moment of 1.8. It boils at much lower at temperature than CCl4 because CCl4 contains more electron. So for that reason, the dispersion forces between CCl4 are stronger than the one dispersion forces plus dipole-dipole forces between CH3F. Okay? Now we will talk about the LDF between an ion or polar molecule and an atom or non-polar molecule. Okay? So what's the meaning of this thing? We will talk about it now. Okay? So if we place an ion or polar molecule near an atom or a non-polar molecule, the electron distribution of the atom or non-polar molecule is distorted by the force exerted by the ion or polar molecule, resulting in a kind of dipole. So the dipole in that atom is said to be an induced or induced dipole because the separation of a positive and negative charge in the atom is due to the proximity of an ion or polar molecule. The attractive interaction between an ion and induced dipole is called ion-induced dipole interaction. And the attractive interaction between a polar molecule and induced dipole is called dipole-induced dipole interaction. Okay? So we need basically to know what is the difference between ion-induced dipole interaction and dipole-induced dipole interaction. Look at the picture basically. For the first one, we have ion-induced dipole force of attraction. It's a spherical atom. We have a spherical atom, and we have upon approach of a charged ion for these electron and these dipole forces, what will happen? It's an approach of a charged ion electron in the atom, and the atom developed a dipole. We have cation and induced dipole. Ion-induced dipole interaction, we have cation and, as you can see, the charge positive, here is the charge negative. Ion-induced dipole interaction, for the second one, when we have the charge positive and the charge negative approaching to the induced dipole, we will call it dipole-induced dipole interaction. Okay, so again, what is the difference between ion-induced dipole interaction and dipole-induced dipole interaction? In the first one, we have cation plus the induced dipole, it will called ion-induced dipole interaction. And when we have dipole and induced dipole, it will called dipole-induced dipole interaction. Summary of LDF. So dispersion forces are attractive forces that it will be as a result of temporary dipole induced in an atom or molecule due to polarizability. Dispersion forces exist among species of all types, whether they are neutral or a pair of a netted charge, whether they are polar or nonpolar. Strength of LDF depends on the number of electrons and the molar mass. The attractive interaction between an ion and induced dipole is called ion-induced dipole interaction, and the attractive interaction between a polar molecule and induced pole is called dipole-induced dipole interaction. Now we will talk about ion dipole forces. What is the ion dipole forces? As you can see, ion dipole forces are forces that attract an ion. It can be cation or ion to a polar molecule. So strength depends on the charge, on the size of ion, and the magnitude of dipole moment and size of molecule. Cations are smaller than anions, so cation interact more strongly with dipole than does the anion. Something it's very important that the cation interact more strongly with dipole than anion. Look at the picture. We have here the positive and the negative. We have the positive here, the molecule basically here. We have H2O and Cl minus and H2O and Na plus. As you can see, the cation are smaller than anion, so the cation interact basically more strongly with the dipole moment than the anion, as you can see. Here is the table of interaction forces. We have the van der Waals forces. We will talk about it now. So van der Waals forces, it's the dispersion forces depend on molar mass and number of mole of electron. B, the dipole-dipole depends on the magnitude of dipole moment. And we have hydrogen bonds depend on the magnitude of dipole moment and size of an atom. Okay? The second, we have ion dipole forces depends on size and charge of ion. Look at the example. We have the dispersion. So dispersion or molecule are end atoms. Look, we have molecule perspective, and the strength, it will increase down. So dipole-dipole will be after the dispersion. We have polar molecules. We have after that hydrogen bonding, molecular containing H bonded with NO or F, and we have finally the ion dipole, which is mixture of ion compounds and polar compounds, as you can see. So as it too, the ion dipole forces depends on the size and the charge of ion. Size and the charge of ion. And something we should know that the strength will increase basically when we move from dispersion, dipole moment, hydrogen bonding, and the ion dipole. Note something very important, that the intermolecular attraction between two ions is called ion-ion interaction, and it's the strongest type of intermolecular forces, not intramolecular forces. And to resume the strength of the intermolecular forces, we have ion-ion interaction, it's the strongest, then ion dipole, then hydrogen bonding, then DDF, then the LDF. Okay? Dipole forces, as a DDF represented by. And that's it concerning the lesson 10.1.